a lot of faith in them.
The Poppleton books are nice. Poppleton Cave. It's Cynthia Ryland. I would look up Cynthia Ryland. She has some very lovely, there's really nice picture books, but there's also nice stories. But Cynthia Ryland is also watching small picture books. So she would go into those again. That's too much.
That's too much, right? Like, I mean, my mom read that for me, though.
Yeah, nobody's going to read her. I would get, some of those. Or maybe
Yeah, what she like. I'm like gonna meet her on Christmas Day, and I want to give her a gift for her.
So, I mean,
Figure maybe. Oh, yeah.
Frozen is popular stuff.
I'm sure she's gonna do that.
Well, picture books are Frozen.
Hi, Meg.
Hello, how are you?
Okay, how you doing?
Tired but good.
All right. Hey, everybody. The whole gang is here.
Hi, I'm Maggie. Do you mind if I sit in?
I'm delighted to have you, Maggie. Thanks for joining us. Hi.
Oh, nice to meet you, Laura.
Laura, welcome. Where are you coming in from?
We're from Menor, Ohio. It's like right outside Cleveland.
Okay, great. All right.
Northeast corner. Yeah.
Wonderful.
Yeah.
Wonderful. Glad you're here. Thanks for coming in.
December 4th. That's gonna be a good week. Because I have a cycle problem that I do too, so it's really sad exam this paper. Well, what if we do the correct part? Yeah, that'd be good. I could probably do that. I mean, significantly in time, so I can't believe our last page. Ew, no, I don't like that. That's like, oh, I'm so excited for this. At the time of the year, it's between now and December. It's definitely we have this week, next week, and no. I'm not because I'm supposed to be here. I don't want to do that. Oh, yeah, I think they went this very excited. Yeah, next week. Yeah. Oh, it's next Wednesday? Yes. Very positive. So, at least before we have to break. Yeah, yeah. It's a good time. Yeah. That would be ideal. That'd be great. Well, Skechers, I had a couple ways to tell my sister to go for break. It's always something, like, after that is and also she does that. Yeah, this is new Doppler Effect. Big time. I just got my first one last year. I felt like I was really behind on the game because my sister had like a year and a half. I know it's really because when I feel like I could do that, like I could do that. I had to like I was like I haven't gone on my next while, so I feel like I'm not.
How's it going? I'm doing pretty good.
I was behind.
Hi, everybody. My name's Nestor. Hi, Tom Johnson. Great. Nice to have you here. Nice to have you.
You were like that.
What about the echolocation? Chirping and everything
I learned about physics, yeah, in high school. I think
I did not pass my electricity and magnetism. I passed it.
did not.
Yeah.
No, I can't connect. Oh, all right.
I was like, isn't here though? The problem
Hi, Claudio. How are you? Good. Want to come in? Okay, we've got 12:30, so why don't we get started? Good afternoon, S&P. Good afternoon. Wow, that's a pretty good response for a Monday morning. I'm delighted that we have several visitors. First, we have visiting with us today Dr. Brooks. We also have some folks coming from the northeast corner. This is Maggie and Laura?
Right.
Okay, and I didn't get all these names. Melissa?
Tom Johnson.
Okay, very good. Welcome. And where are you coming in from?
Virginia.
Virginia. Well, thank you for making the trip. We're delighted that you're here. Just for a little bit of context, this course is Sensation and Perception, and it's an upper-level psychology course. So all the students in this class have had at least our introductory psychology course. Some of them are also psych majors. Not all of them are psych majors. Okay? So it gives you a little bit of the setting. We've also been talking throughout the semester about different senses. We spent most of our time talking about the sense of vision, and at the beginning of last week we transitioned into the sense of hearing. So today we're going to be talking about an important chapter in a book called The Blind Watchmaker. It's chapter 2, it's called Good Design, and the author of this book is Richard Dawkins. He's telling the readers all about the amazing hearing abilities of bats. So hopefully that will give you just a little bit of context for today's conversation. For the students in class, just a couple of reminders. First, thank you to all of you who participated in Friday's discussion in here. That was absolutely wonderful, one of the best conversations we've had. That conversation was about some power and justice related issues that come up when there is a hearing deficit. We had really, really complicated scenarios that we asked the students to grapple with, some moral dilemmas, and they did a terrific job. Then we also were very fortunate to have a visitor. Dr. Stephen Mayer was with us Friday afternoon, and many people in the class were here. So thank you all for coming out. I hope you enjoyed his talk as much as I did. Okay, one other practical bit just before we go into today's conversation, and that practical bit is for Wednesday, we'll have another TED Ed. So the students in this class are completing TED Eds on a regular basis. You've all seen the TED Talks on videos and so forth. TED Ed is a subdivision of the TED Talks, and we can now put up questions that the students will respond to before they come in, and then that promotes the discussion in the classroom. So we're looking forward to Wednesday's TED Ed. It will be more on localization, and we'll be talking about localization a bit today in bats. Okay? So what I'd like to do is have the students work for a couple of minutes in a little exercise that we do from time to time. It goes by the name of When I Teach, I Learn, and the idea is that we have students break into small groups and they teach each other about some of the questions that we've had in our TED Ed presentation, okay? And we'll have the students work in small pairs, maybe twos or threes, and we can have you come up and chat with me about some of these questions also, okay? Do our students have copies of the questions, or do you have access to copies? Many of you have your laptops and so forth, okay? All right, so why don't we do this? Why don't we get into pairs? So why don't we have these two be a pair, okay? And we'll have maybe these, how about these two and those three? I think that works better, okay? Here's a pair, here's a pair, here's a pair, there's a pair, there's a pair, and here's a pair. Did I get everybody? Okay. I think that's, yeah, okay. And then you folks can pair up with me if you like up here. And why don't we do it this way? We'll try to divide and conquer. We have a lot of questions to get through, okay? So I wonder if you're on the door side of the room over here, maybe these groups. Can we have you do questions 1, 2, 3, and 4? You have the questions listed? Can you do questions 1, 2, 3, and 4? Teach each other about those. Okay? And then in the center, can we have you work on questions 5, 6, 7, and 8? And then over here on this side, can we have you do questions 9, 10, and 11? Okay? And I'll keep the questions rolling up here too, just in case anybody needs a reminder. We'll give you about 5 or 7 minutes to chat with your partner about your questions, and then we'll meet back as a group and we'll see what we get. Okay? So go ahead. Go ahead. Do you want to come up so we can? We do a lot of small group work in here, okay? And so the students they get questions like this. So they're prompted with actually a total of 15 questions, and they get these 48, 72 hours in advance, and they begin plugging away on them, and then I can see individual answers, and it really tends to facilitate the conversation. So are you familiar with bat echolocation? The idea that bats echolocate, maybe that's a familiar topic. Yeah, we actually would call it sonar because they send out a sound and they get that back. And what this chapter does is it talks just about the incredible complexity of the biology that goes into that entire phenomenon. The bats can do incredible things. They're trying to catch prey that are very, very small, as you can imagine. And their fishing net is essentially sound, right? So they're putting out these ultrasonic pulses that essentially bounce off of you and come back to me, bounce off of you and come back to me. And as they're putting them out, you can track the rate at which they're returning to you. Now you know that you're homing in on it or it's moving away. And then they have these great capacities that are really on the order of fractions of a millisecond. They can track movements in that really fine time with them. So the students have been answering questions on all the challenges that the bats have.
So this is to prepare for today's class.
Yeah, they've done that for today's class, right? Yep. So and the other part of this is what we would call a flipped classroom. So a couple of years back, I've been here since 2001. I've been teaching this course and on this topic for about 15 years. A few years back, I decided to pre-record all of my lectures. So all of my lectures are up on YouTube. And so when they're answering these questions, there's actually an associated video for most of the questions. And so they can watch my lecture before they come to class. They can answer some questions before they come to class. And now this is almost like our rehearsal, right? So you can imagine that orchestras get to be good because they rehearse well together, right? You can imagine instead that you could just have the conductor stand there and lecture at you the whole time. We're trying to flip it around so that the Dennison classroom becomes fairly active. And the students will feel well prepared for each class because they've had a lot of time to look at this and so forth. So that's how we're operating this time.
Very discussion based.
That's what we're shooting for.
Yeah.
And I've done this for many, many years. And what I used to do is say, well, why don't you just read the chapter and we'll come in and we talk about it.
Right.
And that didn't always work. Not everybody did the reading. Not everybody, some people did the reading, but that was 3 classes ago. They've had a calculus test, they've had a chem test, they've had an art history. Yeah, right. And so they actually remember, if I thought, do you remember the part about when the bat is moving away and we get a Doppler shift? Oh, yeah, but they couldn't generate that, right? So this gives them something concrete to focus on, right? So they have almost like a prepared answer before they come into this.
Is this approach being used in other classes in the department and across Dennison?
This TED Ed is something that I just found out about, something I just found out about in August. I have been making video lectures and flipping my classroom for the past couple of semesters, so I do this. Not all the professors like doing that. It's a lot of time to prepare, right? I also record all of my in-class lectures, so right now we're on my iPad. You can smile at my iPad if you want. And I'm hooked up here, so I don't.
The sound gets recorded.
That's right. So I don't think they might be able to hear you, but they certainly can hear me.
Right. And now, is this a required class for psychology?
It's not. It's not a required class, but it's one of several classes that they can take as an elective. And it can be taken as an elective for the psych major or for the psych minor. I also teach in the neuroscience class. As we're talking about these, you might see some biology-related themes, right? Yeah. And so I also teach in the neuroscience program, and this can satisfy one of the electives in the neuroscience program. We'll go back together, see how we do. Okay, so wow, that was convenient. We all picked up on our cues and the auditory level in here came down, unlike in a bat's cave, and more about the bat's cave later on and the problems that arise there. Okay, so what's not shown here on the slide, there's just a little bit of a preface to this question. We've talked about color vision and the dimensions of hue, saturation, and brightness. Perhaps a blind bat could also experience hue, saturation, and brightness rather than by using vision. But they could do that by hearing, would be the notion there. Okay? So then the question arises, what physical properties of acoustic energy might give rise to the blind bat's perceptual experience of hue? Okay? Somebody over here want to help us out with what you came to? We're looking for some physical properties of acoustic energy. Oh, there's somebody on that side. Well, yeah, I'm going to go over on this. I think this is the side that had that question, right? Okay, go ahead, Claire. Thank you. Okay. Okay.
Definitely the frequency of colors and hues.
Okay, right, so clearly the frequencies, and of course frequency and wavelength are related. Alexa also offered a hand, so we'll see what,
Yes,
okay.
That's, I mean, Claire's my partner, so that's what we were talking about, frequency, just because it's inversely related to wavelength.
Okay.
Wavelength is related to color.
Okay, right, so sometimes a picture will say 1,000 words. For the students in class, who remembers this little ditty? Does that look familiar? Okay, so when a few weeks ago in this year, in this semester, we were looking at the perception of color. We divided it into hue, saturation, and brightness, and we used this graph to talk about wavelengths. And can our students remind us what is the range of wavelengths that humans typically can see? From what to what? Okay. Yeah, you can yell out 400, 700, right? Okay. So we have different spikes here in this wavelength spectrum. So it could be the case that if we have different frequencies of sound, you and I hear those as pitches. Who knows how bats experience them? Maybe bats experience those saliently as colors, right? That's one possibility. So that was the idea about hue. How about saturation? Somebody, Alex has something? Yeah.
I saw it as like broadband sound.
Okay, and can you see what he's doing with his hand? I love the gestures, okay? So, all right, that's broadband. Show me narrowband, Alex. That's broadband. Or there it was, okay, right, okay. So who remembers this little ditty from, okay? If that's red, that's pink. Yeah, okay, that's the idea, right? So red is very well localized. We call this a saturated stimulus, right? I'm very highly saturated, okay? And then we go to here, and we spread it out. We get a broader band, just as Alex had by his gesticulation, okay, narrower or broader, right? So it could be that when they hear something like a sound, which is relatively broad band, they experience pink, okay? And when you've got something like a okay, just a single frequency, they experience red. Right? That could be what's going on. Who's to say what their psychological experience is? Clearly they can respond differently to these, but we don't know about their internal states, and more about internal states in a moment. So we did hue, we did saturation. What's our last one? Brightness, okay. And what's that going to look like from a physical property standpoint? What's the physical property that we're going to get there? Go ahead, Zach, that's okay. Okay, it would be loudness, right, which would be amplitude, right, or intensity. And back in the color domain, we might say if that's red, we're going to leave it localized exactly where it is. It's going to be at the same wavelength, but we can do this. We can now bring that down, and we've gone from red to maroon. The only thing that's changed is the amplitude, okay? So maybe the bat is having an experience like that. They're actually experiencing a red to maroon difference just by a change in the intensity of the acoustic energy in this case. And we use these back in the domain of vision. Who's all right with all that? Any questions on that interesting possibility? We have a lot of questions, and so I don't want to have us get off track, but I can't help trying to make a connection here to the doctrine of specific nerve energies. Does anybody remember hearing about that in Intro to Psych, first, second, or third chapter? The doctrine of specific nerve energies. We haven't, I think, mentioned it in this class, but I talk about it in my Intro to Psych class. Yeah, some people are smiling.
Some of them know for sure.
Some of them know for sure. Is that the History and Systems group?
Yes.
Okay. Some of our students are seniors, and they're also taking, so our visitors will know who's on the in-joke here. Right? Dr. Brooks is joining us today, and he teaches history and systems, so he knows some of the students of the class are on to that one. Go ahead, Meg.
How we can choose different nervous sensory systems, and through that, whichever system is being activated is the type of stimulus.
Right. So whatever system is being activated, that's going to drive what kind of psychological experience we're going to have. If our optic nerve is being stimulated, we're going to have a visual experience. If our acoustic nerve is being stimulated, we're going to have an auditory experience. Those are the second and eighth cranial nerves, respectively. Okay. But interestingly, on some level, on some biological level, it's all neurons firing. On the optic nerve, we have neurons firing. On the acoustic nerve, we have neurons firing. So why would one of those generate sound to us perceptually and one generate vision to us perceptually? And the idea is simply it depends on which of those nerves is going, and that's the doctrine of specific nerve energies. Does anybody remember who gave that to us? Now, there's a historical question. Who is the one who is the proponent? Yeah, please. Mueller. Wow, okay. All right, so you did your due diligence in history and systems. So let me just show a brief connection here. I think I've got it in one of these. Okay. So here's my academic tree, right? I went as an undergraduate to one school. Here's my doctoral lineage. Here's my postdoctoral lineage. You can see that I'm all the way at the bottom of this tree, and because you are my students, you are now connected to Johannes Mueller. Here's me, okay? Here's my undergraduate teacher. Here's that person's teacher, that person's teacher. We all go back to Johannes Mueller. over on this line, and I think we make a connection to Johannes Müller one more time in my postdoctoral line. So you now have multiple lines of connection to Johannes Müller, who gave us this doctrine of specific nerve energies. It's all neurons firing, so it might be the case that the bats are actually experiencing color when you and I are experiencing pitch. Okay? Pretty cool. Pretty cool that possibility is there. Who's following that? Yeah? All right. Okay, away we go to question number 2. Okay? So here's Dawkins. He's saying this: bats use noises vastly higher than the highest note anybody, meaning any human, has heard or can imagine. This implies there's a limit to how high a note we can imagine. Do you agree? Okay, so this is just a subjective answer there, whether you agree. And why would our auditory imagination be limited by what we can actually hear? So let's see if anybody grappled with this one. Is there a limit to how high a note we can imagine? Okay, Claire, go ahead.
We talked about how we did agree with Doctrine.
Okay.
That there is a limit based on our imagination that we can hear, just because when I think of it, I think about color, especially if you're taking information about what you already know
Uh-huh.
into account. So if you don't have any sort of information about your imagination's probably based in the experiences you already have. So if you've never heard anything like this sound before, it would be really hard to conceptualize.
Okay. Okay. Right. So maybe we do need the experience in order to have the imagination. That's one viewpoint. Some other ideas on that? Some other ideas? Yeah. Okay. Any experiments that could support or falsify the claim that there is a limit to how high a note we can imagine? Anybody think of an experiment that we could conduct that might investigate this claim about there being a limit on how high a note we can imagine? So here's the word imagine. Who remembers some earlier experiments this semester on imagery? Does anybody remember that we had, and can somebody remind us how the imagery experiments worked? But that was visual imagery. This is almost auditory imagery, right? How high a note can you imagine? Okay, go ahead, Molly.
So we sort of had a grid with 4 different stimuli. So one in the far left quadrant, and then there were 4 different stimuli, and they each differed qualitatively. Some of them had like different numbers of stripes. Some of them had they were like shifted diagonally.
Okay.
And we were shown this stimuli with 4 quadrants for like a given amount of time, and then we were asked to close our eyes, and then we were asked, did the stimulus in quadrant 2 or quadrant 3 have more lines? And we had to sort of.
Okay.
So there was a correct response, but we had to use visual imagery to override that correct.
Okay, right. There was a correct response as to type A experiment. We distinguished in the early part of our semester type A experiments, which have factually correct, demonstratively correct responses, versus other kinds of sensation and perception responses, type B responses, that are very subjective. Do you find this drink to be too sweet, too hot, too cold? Those are important questions on some level, but they're very subjective. Here we have an objectively a verifiable kind of response that could be made. And this was done by Steve Koslin. And what else was going on in that Koslin experiment? That was a beautiful description of the behavioral component. What else was going on in that study? Does anybody recall? Go ahead, Alexa.
They were in an fMRI.
They're in an fMRI, okay.
And it showed that the visual cortex was active.
Right, so even when we close our eyes and we're not driving any activity back here in the primary visual cortex with the stimulus-driven information, if you're asked to all of a sudden start using visual imagery in order to answer a question that has verifiably correct or incorrect answers, you all of a sudden turn this on and this thing starts working for you, even though it can't be driven by the optic nerve, the thalamus, and that connection, right? It has to be driven now, if you will, by imagination. That gives us visual imagination. So you can imagine a simple counterpart over here, where we can ask you to imagine a soprano singing a relatively high note, okay? And then maybe we'll get some activity in your auditory cortex, even though there's no sound in the room at the time. Okay, then we ask you to think about a higher note and a higher note, and at some point maybe we ask you to keep on thinking of higher and higher notes, and we don't see any corresponding change in neural activity. Right? That might be an indication that really, if you can't experience it by having some kind of activation in your auditory cortex, maybe you can't even imaginarily hear it. It's an interesting question to muse about. Okay, now back to a little bit of the physics over here in question 3. The intensity of a sound decreases with the square of the distance from the sound source. This is a basic physics principle called the inverse square law. Okay? This sets up a paradox, a physical constraint on the physiology that makes echolocation possible. Can somebody help us out with that? What's the paradox that we have that comes about because of this physics problem, the inverse square problem? Okay, Alexa, go ahead. Thanks.
The sound must originally be very loud in
Okay.
order for it to still be making any noise when it gets back to you, but your hearing system, your ear must also be very sensitive in order to pick it up when it comes back. So
Okay.
how do you make a loud noise without damaging the...
Okay, right. And Meg also had a hand up. Was that what you were going to offer? Something along those lines? Right. So the idea is, if I really want to bounce some sound off of that back wall, and by the time it reaches the back wall, it's going to be diminished in intensity by the inverse square law. It's going to be 1 over d squared, and then that sound has to bounce back and come this way. So it's traveling really twice the distance, okay? So I'd like to get out a really, really loud sound, a lot of intensity. But if I have sensitive ears, I might blow out my ears, okay, right? So there's that problem. I don't want to blow out my ears, but I need to get some sound back. Okay? You might remember this one. Some people have seen this movie. People know this. You'll shoot your eye out, kid. Yeah? Okay. Well, the bat has the problem of you'll shoot your ear out, right? If you put out a sound that's too loud, you could wind up shooting your ear out. Who appreciates that problem? Yeah? How many people have seen this movie, by the way? I think this is a Christmas Story, yeah? And I think this takes place in the movie, I believe it takes place in Indianapolis, but I think it's actually shot in Northeast Ohio.
Cleveland.
It's shot in Cleveland? Okay.
There's a museum there now.
There's a museum about shooting your eye out
You can
and
go
shooting
buy
your...
a red lamp.
That lamp's pretty outrageous. All right, okay, so we have to avoid shooting our ear out, and that brings us to question number 4. What is send-receive radar? And I think, let's see, are we into, this is the last question for the door people. Anybody have send-receive radar? Okay, Alex, thank you.
It's when, I guess the question is, when we talk about radio towers, the aerial, which is the highly sensitive input, is temporarily switched off just before the radar pulse is emitted to avoid damage.
Okay.
So it's back on to receive the signal.
Yeah, right, okay. So we have this way of turning on and turning off basically our own sensitivity. At least we can increase it or decrease it, right? So we can momentarily deafen ourselves. We talked about the acoustic reflex last time as a way of momentarily deafening ourselves, right? And this can happen many, many times per second. Another example of the tremendous biological complexity that bats can use. Remember, they're putting out pulses that are going to be on the tens of thousands per second, okay? So you can imagine how difficult that is to have your ear momentarily deafened and then made sensitive again, deafened and sensitive over these almost unimaginably small units of time. Okay. All right. So one other question just about evolution now. Could this have evolved by random mutation alone? Anybody want to help us out with that? This tremendous biological complexity of this acoustic reflex that shuts it off, turns it on, shuts it off, turns it on many, many thousands of times per second. Go ahead, Meg.
No, because the kind of like two-step engine, I guess you called it, for evolution was that you have random mutations, but you also have non-random selection.
Okay, right. Can we all say that together? Non-random selection, everybody? Non-random selection. That's actually what's going to get us our accumulation of biological complexity. If we had to start with an ear every time from scratch, we had to try to build up an ear from scratch every single time, we'd never get there. But if we can inherit some non-random mutations, right, that have been selected because of their fitness, then we can build up generation by generation this tremendous biological complexity that allows these bats to do all these cool things. Okay, thank you to the door people for handling questions 1 through 4. Now we're on question 5 through 8, and this is going to be in the center. So here's another issue for us. If a bat has trouble detecting faint echoes, why can't the bat just increase the duration of the sound it emits so as to produce more energy to be detected by the echo? So why not just go for a longer period of time? Okay, now we have a new set of hands. We'll go this time with Abby and then with Gabby.
I said like it wouldn't work because if a bat like emits like a longer drawn out sound, it would be more difficult for it to produce like an energetic echo that would like a good sounding energetic echo.
Okay, if it's really short, it's hard to get a lot of energy going. If it's really short, okay. Did you want to add something to that?
I was going to say that also measures the amount of
Yeah. Right.
And if they were making out the sound that was really long, it might bounce back while they're still making the sound.
Yeah, right. Right. So our preceding question was about send, receive, and we're in this mode all the time. We're in this mode presumably several thousand times a second. We're either in send or we're in receive. And we need to be doing both of those things several times a second in an interdigitated manner, okay? So yes, I could make the sound more energetic by giving it a little bit more time, but that means I'm missing opportunities to pick up the sound. And it might be the case that if I'm a bat, my flying insect that I'm hoping to get for lunch is now going to move away if I'm still putting the sound out. I need to be able to send and receive in an interleaved manner, okay? So one fun bit about this is a diagram that you might remember seeing before. Who remember seeing this diagram before? Okay? Can anybody recall where, a little memory test here, I always like to have my students try to connect back to earlier parts of the semester. Where did this thing rear its head? And what is that thing anyway? Anybody recall? Okay, go ahead, Abby.
What's the line with the Fmri and the TMS, and you talk about like how the Fmri we can just like monitor different like, or how like TMS we can like manipulate different like brain mechanisms,
Right.
or like Fmri we just like consider.
Yeah, right. And this too, that's exactly right. This too comes from the Koslin experiment. We were just talking about auditory imagery and visual imagery and so forth. So this too comes from the Koslin experiment. Koslin, as Melanie and a couple of students worked their way toward the answer of having area V1 turn on when we're doing visual imagery. Here what we can do is actually apply a magnetic pulse. This is called a transcranial magnetic stimulator for our visitors. And when we were talking about visual imagery, you can actually disrupt your visual cortex by putting on a pulse. And the pulse sounds like this. It's about that loud. Which doesn't sound all that loud. Actually, it is 140 decibels. So how can this be 140 decibels? For reference, 140 decibel sound is what you would experience if you were about 10 feet away from a jet engine on a 747. Tremendous amount of, again, it's only this loud. And the reason is that this TMS device is firing only an interval of about a few microseconds. Okay? It's not even a millisecond long. It's some fraction of a millisecond long. So there's not a lot of time for this 140 decibel machine to get up a lot of energy. Right? So you can imagine that this poor bat is trying to send out a very energetic bit, but it has only this small window of time in which to operate, and it has to get back into receive mode really, really quickly. Okay. All right, here's the chirp. We've got the chirp radar, the chirp sonar. What can that do for bats? Jess has something, and then we'll go to Melanie.
The bats produce like a series of pulses that they all have different pitches, and so the bats are able to tell different echoes from each other.
Okay. Okay, they can tell because of the different pitches. Okay. So and did you want to add anything to that?
I was just saying, like, the frequency, like, swoops up or down.
Okay. By about how far, Melanie? It swoops up or
Like, it's
down?
an octave.
But by about an octave in most species. It differs by the species, okay, so it swoops up and down. I wonder if Melanie and Jess can help me. You tell me what to put up here. If I wanted to draw the chirp, okay, I wanted to make a graph of the chirp, I was thinking about doing this as a draw-to. For some of my questions for the visitors, we have the students go onto an online drawing board, and they make graphs and so forth. So if we wanted to draw the chirp, can you tell me, like, I don't know how this is going to work, so why don't you tell me how I would graph the chirp? I'll give you this much. What goes where? And you can help them out. You can yell out what has to go. What would be on this axis? What would be on that axis? Okay. Time? Okay, thank you, Molly. So here's time. Okay. This is the passage of time across this. And we could specify what the unit might be. It might be in milliseconds. It might be in seconds. It could be in microseconds, given how fast these animals are moving. Okay. So time is on this axis. What's going to go on this axis? Frequency, is that working for us? Okay, so that's what the swoop is, because we talked about that the animals will be chirping over something like maybe an octave. Okay, maybe an octave, all right? And what will my graph form look like? I've got frequency over time. Okay, can you draw it in the air? I should draw it in the air what the chirps would look like. Let's say that there were 3 chirps up here. What would the chirps look like? Okay, some of us are getting there. Some of us are waving our hands. Okay, all right. How about, let's say, I think many of the species go with a downward chirp. Let's say it's something, I'm going to make it somewhat linear, like that. Okay, and you can almost hear it. Okay, now if I put out a, and 2 echoes come back, and one is higher and one is lower, the higher pitch must be further away. Right? So these bats are very clever. They have a way of almost, if you will, color coding what's coming from where. Because back earlier in time, I was at a higher frequency. At the end of my chirp, which is a little bit later in time, I'm at a lower frequency. So if I get 2 echoes coming back at the same time, and they're of different frequencies, I have some idea about which one is coming from the more distant object and which is coming from the nearer object. Right? So the rule of thumb here would be something like higher is further. Yeah? Is that working for us? Okay. And of course, some other species of bats might have not a, but they would have a, and then this rule would reverse. Then lower would be further. Okay? But it doesn't really matter which way that particular species converged. As long as they've got that chirp, they can figure out how to unpack this sea of otherwise chaotic echoes. Yeah? Is that working for us? Okay. All right, I think we're still in the middle group. What is the Doppler shift? And what does that do for bats? Doppler shift? Okay, Abby, thanks.
It just says that like the sound increases the object. Like the person exposed to the sound, the back exposed to the sound.
Okay, right, so there's going to be this change in frequency as we're homing in on something, right? As I'm getting closer, if I'm putting out the same frequencies, I'm going to get some kind of an elevation in the frequencies that are coming back, and I'm going to hear this upward swooping sound or this downward swooping sound. And based on that frequency modulation, whether the pitches are going upward or downward, I have some idea about how far my target is. You know, am I getting closer to it? Is it pulling away from me? Okay, maybe the insect is taking evasive action. Right, the insect might be taking evasive action, and it might be the case that I'm putting out a constant sound, and it's now getting lower and lower pitch. That means that animal's getting away from me. Okay? So I can use that as a way of determining how far I need to go to catch that animal, or if I need to change direction or speed up or slow down. All kinds of information is conveyed by the Doppler. Who's all right with that? Okay? We could spend a lot of time. We could spend an entire session on the Doppler effect. Lots of interesting phenomena. I did find a couple of videos, and I'll try to keep them brief, but some of these are just too interesting. They're about the Doppler, and they're also about this problem of RoboCop. Who's heard of that as a movie? RoboCop? Yeah? Have you heard of RoboCop? Some people are laughing.
Some of us grew up with RoboCop, yes.
Okay, some of us grew up with RoboCop, yeah, so some of these references are a little bit dated, but RoboCop is a really interesting idea that relates to the Doppler shift. So here what we have, it's kind of like the World Cup of soccer, but these are now robots that are playing soccer against each other. So this is called RoboCup, right, like the World Cup and RoboCup. But the idea becomes, well, how do these robots solve all kinds of interesting sensory problems? And the answer is they're going to try to mimic the bats. They're going to try to use some kind of either sonar or radar and take advantage of the Doppler shift. So when you're playing soccer, you need to keep track of where the ball is. Sometimes you're coming up on the ball. Sometimes the ball is moving away from you. Okay? You can use Doppler technology to figure out where you are relative to that moving target. Who's all right with that? Okay? Something else that soccer players have to do, either real or robotics, they have to know where their teammates are. Okay? They have to know where the defenders are and so forth. Okay? So you can send out all kinds of either electromagnetic energy or acoustic energy. You get that information back. It's going to be Doppler shifting in every possible direction. Okay? And this is a way of keeping track of relative position over time by using Doppler shifting technologies. Who's following that? Yeah, okay, so the bats got in on this thing early. It's tremendously informative. Okay? All right, I want to show you these other two videos in this context. As we were coming in today, I was playing a song by Bob Marley. Did anybody pick up on what the song was? You Be Jamming, okay? So what is jamming in bats and echolocation? Go ahead, Liz.
So it does not deal with other sounds that are present when I'm making their chirping sounds, and a lot of the time the jamming is actually other bats trying to also echolocate.
Okay.
And so I gathered from the article that scientists weren't exactly sure how they solved this problem, but they thought that bats each had their own frequency, which they could somehow pick out.
Yeah, right. So it could be the case that I'll send out a frequency when I go to my car. Here's my car key, right? It's got many of us have these electronic car keys. So you might say, well, how does my car know that this is me, and when Jess is going to her car and she has one of these two, how come my key doesn't open her car? They all have very specific frequencies. So one of the ways that the bats might solve this problem is maybe I've got my own private frequency. That could be the case, but remember, we're sweeping over large range of frequencies, and so are you, right? So it might be that that could have worked, but maybe that's not what's going on. But that was one idea that scientists had. Jess has something else.
We're talking about
The strangeness filter.
So like the bat, you previous echoes kind of show this bigger picture, and if you receive like an echo from another bat, it won't fit into this bigger picture of what they're trying to evoke.
Okay, right, yeah. So we have to have some kind of coherence in our representations, and there's a slide coming up here on representations over time, right? It has to make sense given the recent history of echoes that we've just had. We can't have one that's completely out of the sequence. Zach, did you have your hand up a moment ago? Okay, we could say the same thing. Right? So it's interesting. As I'm standing here, I'll be stationary just for a moment, and then I'll begin to move. And as I'm moving, the information on my retina is changing. But it changes relatively modestly for any given step. It's not like all of a sudden I get the picture from where Claudio is sitting, right? It's not like I get his picture all of a sudden. Any one picture is pretty similar to any other one. And if all of a sudden you get an echo that's just not making sense, the thinking is that the strangeness filter, however we might implement that biologically, will get rid of that thing, okay? So that you have a coherent sequence of acoustic images, one after the next. So I will interrupt us just for a moment because I think these videos are so cool and I hope I can get them to work. Okay? We're going to talk about or show you two different kinds of jamming related videos. In one of these, we have a defensive move. This is so cool. The prey are going to take a defensive move against the bat that's coming to get them. So the bat is echolocating. The bat is probably using this chirp, right, this frequency modulation, sometimes downward, sometimes upward. It's coming in. And some of the insects have developed this sort of missile defense system. Okay, they're going to deliberately jam the bat's sonar. So I'm going to turn this down just for a moment at the risk of losing some folks. Okay, and we'll see if we can get this going.
Slow motion night vision technology allows us a glimpse inside the bat's world. Sonar detects insects in complete darkness. A big brown bat targets its prey and locks on.
Can you hear it crunching the prey? You hear it again. It's actually crunching the prey. Here we go. Crunch.
But new science reveals that the tiger moth has a secret weapon. Ultrasonic sonar jamming technology. Its high-speed clicks are slowed down so we can hear. When a bat locks on, this moth fights back. For a moment, the bat is truly blind. The jammer moth uses a sophisticated strategy to survive. But other deserts present even greater challenges.
Okay, so you get the idea, right? So that's a pretty sophisticated response. I loved what they call it. So you see this moth, and they described it as ultrasonic sonar jamming technology, and they've got that on board. They've got that mid-flight. I think that's really, really cool. I wanted to show you one other variant on this important topic of jamming. So there's an arms race going on here evolutionarily. Right? So over millions of years, these animals are developing this anti-missile defense system and how to get around that and so forth. Now here's another one. That was now bat on insect. Now we're going to see some jamming that's bat on bat. Imagine that Melanie and I are bats, and we're going after that particular piece of prey, and she's got her eye on it, and I've got my eye on it. She might be able to jam my sonar so that she can get it and I can't. Okay, so this is now bat on bat, deliberate jamming, if I can use the word deliberate. This is from Science.
Mexican free-tailed bats have figured out how to turn that dream into a reality. They jam each other's bat signals, but not because they're trying to turn down the volume. They're just trying to steal each other's meals. These bats hang out in colonies that can number in the millions, but living with so many relatives can lead to conflict. When the colony swarms out to feed at night, competition is fierce. To get an edge, the bats jam the sensory equipment of nearby buddies. Then they can swoop in and steal the meal for themselves. Echolocation is basically biological sonar. First you emit a sound, then you listen for an echo, which tells you the position and speed of things around you. And just like sonar, bats can all listen in on the same channel, at a frequency mostly above the range of human hearing. This is the sound of a free-tailed bat getting closer and closer to its target. Often a farm insect, while still an orderly sound like a normal echolocation call, the audio pulses speed up because the bat needs to get more information quickly as it nears its prey. Unfortunately, the speeding buzz also lets nearby hunting bats know that a competitor is close.
Here comes Melanie.
Using triangulation, Aaron Corcoran and William Connor were able to show that when nearby bats hear the buzz, they swerve from their flight and hone in on the hunting bat. As these interfering bats close in, they actually try to disrupt the hunt by emitting a jamming call of their own. These vocalizations swoop up and down like a siren, covering all the frequencies made in the feeding buzz. The jamming call causes the hunting bat to lose track of its prey, and the jamming bat takes the opportunity to snap it up. We don't know whether other types of bats are using jamming to steal food from one another, but now researchers know to look out for this new adaptation in highly competitive feeding environments.
Okay, all right, so that's our second video on jamming. Okay, so sometimes it's prey on predator. These animals are trying to survive. Other times it's competitors. Okay. And this raises some interesting questions. You just correctly mentioned a moment ago the strangeness filter. So not only are these bats going to have to somehow get into the right frequency range. Here comes Bat Melanie, okay, and she's going to now put out some acoustic energy that's going to try to mask over whatever signals I might have been sending out that way, right? And somehow, not only does that mask things, but it somehow makes it through my strangeness filter, okay, so it doesn't get filtered out, and it's enough to throw me off, and then she grabs the target. Pretty interesting. It's almost as if these animals are fishing with acoustic nets. They're trying to catch prey, and their nets are not made out of string like ours would be, but they're made out of sound. Right? They've got these acoustic nets, and they're jamming each other with these. Questions or comments about that? Some people think they follow those principles. They understand what's going on there. Okay, we have a couple of minutes left. Why don't we do another question or two? We won't make it all the way through, but we'll pick it up on Wednesday also. So that was jamming. And we talked a little bit about having some kind of representation that might match or not match what's coming in, and we have the strangeness filter and so forth. So he's suggesting, Dawkins is suggesting, that maybe the animals build up some kind of internal representation. Somebody tell us what that might be. What would be an internal representation? And what might Skinner say about that? Was that a hand? Yeah, okay, thanks, Isabel.
What I understood was the way that a species uses the incoming sensory information that they detect, and Skinner was able to consciously know like the nature of that because his behavioral study.
Okay, so there's a lot there. First, let's spend a moment on the representation, right, and the internal representation, and then we'll pick up on your point on Skinner, right? So there are different ways of thinking about representations. Who remembers hearing about analogical representations or symbolic representations? Okay, right? So whatever kind of representation it might be, we can think of a representation as being a correspondence between two systems. That, I think, is the cleanest definition I've heard. I've taken a lot of psychology classes in my day, and people throw around representation, and a lot of times I don't know what they're talking about, and I sometimes suspect they don't know what they're talking about, but there was one cognitive psychologist from Rutgers one day who was giving a talk at Brown when I was there, and he defined representation as a formal correspondence between two systems. Simple example would be a map. So our visitors came on campus today. You come up from the parking deck and you see, here's the big map, you are here, right? The state of that map can tell you something about the state of the campus. And where you are on that map tells you about where you are on the campus. So one idea would be that our brains perhaps have representations, correspondences to things out here in the real world, and that is now, of course, very internal, and Sibel correctly made the point about B.F. Skinner. Can you say just a little bit more about that? So you said, well, he was a behaviorist, and I know what you mean by that. Can you unpack that for us?
He was a behavioralist, and behavioralists didn't really believe in like kind of cognitive psychology or like processes, and I feel like it just everything happened because of external.
Okay, right, and he limited his domain of investigation to that which can be readily demonstrated, right? That which we can see or hear or somehow get some kind of instrument that can verify it. If we start talking about internal representations, some of these folks would say, well, maybe we're going to get away from falsifiability, right? And maybe we're going to start speculating beyond what the data would allow. Okay, our question number 10 will take us into just another problem that will eventually lead us to some logical fallacies, and we want to spend some time on the logical fallacy that this chapter ends with. But we're out of time for right now, so why don't we pick up our conversation on the reflective bear and the logical fallacies on Wednesday, all right? So look forward to that conversation. I realize some folks need to set up next door for the S&P research group, so I'll be over there to help you if you need some help. And I look forward to seeing everybody on Wednesday. Special thanks to our visitors for coming in today. Thank you.